In this presentation, I'd like to offer a brief introduction to the physics concepts of stress and torsion, and then discuss how those relate to the rear naked choke, also called the lion killer or mata-leão in Portuguese. I'm Mark Bauman. I'm a research fellow in physics at the University of Texas at Austin and adjunct professor of physics and astronomy at St. Edward's University. And I am also a Brazilian Jiu-Jitsu purple belt. So if you haven't already watched Renee's video where he demonstrates his version of the rear naked choke, please watch that video first and then come back to this one. Okay, to start, let's talk about these concepts of stress and strain. I'm going to keep these simple and give you a kind of a brief one-word definition or few-word definition for each one. So strain is a stretch or compression. So you can think of strain, stretch. There's a lot of STR words here, strain, stretch, and stress, and it can take some time to get used to all of these similar sounding words. But strain is a stretch or a compression, and a stress is something that causes a strain. So stress is something that causes a stretch or a compression. These concepts are perfectly general for any material. So we could be talking about a rope, we could be talking about a cable or a column that's holding up a building, a post that's holding up a fence, a bone, the human arm, including the bone and the tissue around that, the human spine, the neck, a column of fluid underwater, a column of air in the atmosphere. So these concepts apply to all of these different things. So I'm just going to draw these as a cylinder. Okay, so take these cylinders here, for example. They could be, let's say, a rope. And they have the same cross-sectional area. So we have two ropes of equal thicknesses. And we're pulling on these ropes with different forces. So I've got force 1 and force 2. So we're pulling more on rope number 2. Force 2 is greater than force 1. So which of these ropes is going to stretch more? I think that it's pretty intuitive that rope number 2 is going to stretch more. We're pulling on it more. We're pulling harder. Therefore, it's going to stretch more. So that we can interpret then is since there was more stretch, that means more strain, must have been caused by more stress. So the more force we pull it with, the more stress we are applying. Okay. Now, what about the areas? Let's say that now we keep the force the same on two different ropes. We're pulling equally on two different ropes, but the ropes have different cross-sectional areas. One rope is thick and one is thin. So rope 2 is the thicker one. And we pull on these two ropes with the same force. Which one's going to stretch more? Again, I think intuitively we would agree that rope 1 would stretch more in this case because it is thinner. The thicker rope is going to be harder to stretch than the thinner rope. So if we pull on them equally, the thinner one should stretch more. So I can summarize that by saying that since rope 1 had more strain, then rope 1 must have experienced a greater stress. And so less area would lead to more stress for the same force. So I can summarize all of that with a simple formula. Stress, which we represent with the Greek letter sigma, is force divided by area. More force is directly proportional to stress, so more force means more stress. Less force, less stress. Area, it's inversely proportional to area because area is in the denominator, so more area makes that a smaller right-hand side, which is going to make the left-hand side smaller. So more area, less stress. Less area, more stress. And if we look at the units of this for just a second, so stress is force over area. Force could be measured in pounds, and area could be measured in square feet, for example. Or force could be in pounds and area could be in square inches. So stress would be measured in pounds per square inch or PSI. Or if we're using metric, force would be in newtons, area would be in meters squared, and a newton per meter squared is what we call a Pascal. So you may recognize these units, Pascal and PSI. Maybe you recognize one or the other or both. And that's because these are the same units that we use for pressure. And the reason is that pressure is also defined as force per area. And so I'm going to come back to that in a minute and talk about what is the exact relationship between pressure and stress. Another concept that I'd like to talk about is this idea of energy density. Physics is, in my opinion, the study of energy. A lot of people think of physics as the study of force. And that's because that's the way introductory physics is usually taught. You start with force. But eventually in your physics education and physics career, you reach the point where you really think about things more in terms of energy than in terms of force. And I think that physics is the study of energy. So physicists love to talk about energy, and we're going to do that today too. So this word density, though, let me start with that word. Density means, in our everyday language and in science, it means per volume, right? So when we talk about the density of an object, we're usually talking about the mass density. We're talking about how much mass per volume that object has. Something that's more dense has more mass and a smaller volume. Something that's less dense has less mass in that same volume. We also sometimes talk about population density, and there we're talking about people per volume or people per area. And similarly, we can talk about energy density, which is energy per volume. So we're talking about how much energy is packed into a particular volume. That's the energy density. Higher energy density means more energy is packed into the volume. And I just want to take a look at a quick algebraic demonstration here. So I use the Greek letter rho, looks like a P, to represent energy density, and it's energy per volume. So energy divided by volume. And energy can be thought of as a force being applied over a distance. So a force times a length. So I've taken E and I've replaced it with force times length. Volume can be thought of as an area times a length. So I've replaced the volume with A times L. And you look at this fraction, you see that the L's cancel. And we're left with force per area, which we've seen before. So energy density is also measured in pascals or PSI. And so what I'm getting at with all of this is that these are all different ways of expressing the same thing. Stress, pressure, energy density. Another one that physicists like is momentum flux per second. That's a little more complex. I'm not going to talk about that right now. But all four of these phrases are different ways of expressing the same thing. So the bottom line for this particular presentation is that when we talk about stress, we are talking about how much energy is packed into a volume. So there's two types of stress. The first one is normal stress. And in this case, normal is used in the mathematical sense of the word normal, which means perpendicular. And in normal stress, the forces are perpendicular to one or more surfaces of the object. So here I've drawn the object as a cube. You'll see why in a little bit, why I chose a cube. It's a very simple three-dimensional object, and we're talking about things in 3 dimensions. And also a cube serves as a nice kind of building block for more complex objects. We can think of complex objects as being composed of many small cubes all stacked together, kind of like Lego blocks. So let's focus on what happens to a single Lego block, and then we'll look at what happens to the entire object that's made out of these Lego blocks. So in the case of normal stress, we're applying forces perpendicular to the surfaces of the cube. Those could be pointing inward, which would cause the cube to get smaller, compressing the cube. They could be pointing outward, in which case the cube would expand. That might be a case where you have, for example, a gas inside of a flexible container that's expanding. And you can possibly have both at the same time. So in my bottom right drawing there, I have that it's being compressed in the horizontal direction, it's being stretched in the vertical direction. So we have a stretch and a compression. It's kind of pancaking this thing. But these are all examples of normal stress, because the forces in all of these drawings, every force arrow is perpendicular to a surface of the cube. And now I can tell you what the relationship is between pressure and stress. Pressure is just normal stress. They are the same thing. We use these two different terms basically to refer to two different types of states of matter. If we're talking about liquids and gases, we usually use the word pressure. If we're talking about solids, we usually use the word stress, normal stress. But they are basically interchangeable. And that's just convention that solids, we talk about it with one phrase, liquids and gases with another, but we can flip those two if we like. They really are the same thing, pressure and normal stress. The second type of stress is shear stress. So whereas before we had forces that were being applied perpendicular to the surfaces, now we have forces being applied parallel to the surfaces. So in my drawing here, I have a force acting on the top surface to the left, and then a force acting on the bottom surface to the right. So you can see how those arrows are parallel to the surface that they're acting on. And this is going to cause a deformation. So this cube is going to turn into a parallelepiped. A parallelepiped is a parallelogram in 3 dimensions. So it's easy to demonstrate this with, for example, a deck of cards. So if I take a deck of cards and I apply a force sideways to the top, so parallel to this top card, and I'm going to go ahead and just kind of push them over like this, and this is what shear looks like. Okay, so we have something that's cubic or rectangular here, and we slide the top with a force. We apply a force on the top, and it's going to deform it like this. Okay, so that's shear stress, and I just want to make this quick mention that normal and shear stresses are all that there is. Those are the only types of stress. And you may wonder, well, what about a force that is neither perpendicular nor parallel to a surface? Maybe it comes in at an angle. Well, that is both a shear and a normal stress. So there's a component of that stress that is going to cause it to shear, and there's also a component that's going to cause it to compress or expand. So it's both a normal and a shear. So we can think of all stresses as a combination of normal and or shear stress. Okay. So another concept that I want to introduce is torsion. So torsion, in one word, is a twist. So for example, if I hold one end of this bar stationary, you can see in this animation, while I twist the other end of the bar, we get this twist, this torsion. This is just like when you open a jar. When you open a jar, you hold the jar, so you're holding the bottom part of the jar stationary as you're twisting the top part. Okay, so that's a torsion. And you don't have to hold it stationary. You can twist them in opposite directions, and that's still a torsion. But holding one end stationary and twisting the other end is an example of torsion that we're going to look at today. I can also do this with a deck of cards. Again, the cards are not held together, but I can still kind of simulate this idea where I'm going to hold the bottom of the deck stationary while I turn the top of the deck. And so I'm twisting the top of the deck. And so I'm getting this torsion, this twist to the deck of cards. So let's take a flexible cylinder and dice it up, divide it up into cubes. And so these cubes are serving as a visualization tool. We don't actually have to have a cylinder that's made of cubes. We're just doing this for purposes of understanding what's going on here. So we're using the cubes as a visualization tool. You can think of them, like I mentioned, they're like Lego blocks. These are flexible Lego blocks that have been stacked together to make up a cylinder. So now what happens when we twist the top of the cylinder while holding the bottom fixed? Well, we get something that looks like this. And notice what's happening to the cubes. They are shearing, right? They are being deformed into parallelepipeds. So this is a shear force that this torsion is causing. So torsion causes a shear stress, and that's illustrated with this with these simple drawings. To kind of summarize all of these physics concepts, when you apply to a normal stress or a shear stress to an object, they can both increase the energy density within the object. And a torsion applies a shear stress. So the chain of reasoning down here is that a torsion causes a shear stress, which is another way of saying that the energy density in the object has increased. Okay, so how does this relate to the rear naked choke? First, let's talk about the purpose of the rear naked choke. The goal here is by wrapping the arm around someone's neck, you are applying pressure on the carotid sinus and on these baroreceptors that are on the carotid sinus, which signals the brain that the blood pressure needs to change, and that causes unconsciousness. It's very similar to fainting. Renee has written a really great blog article about all of this, so I recommend reading that for more details. But for our purposes right now, let's just note that the goal of a rear naked choke is to apply pressure to the carotid sinus. So in the traditional rear naked choke, that arm is wrapped around the neck and they squeeze. And so when they squeeze, what they're doing is they're causing a compression of the neck, right? And that is a normal stress or a pressure. Remember, those are the same thing. So by applying pressure to the carotid sinus, that is one way of performing the rear naked choke. An alternative is, as you saw in Renee's demonstration, is that you don't have to squeeze. You can just twist. Why does that work? Well, based on what I've presented and argued so far, a torsion, a twist, is a shear stress. And a shear stress, like a normal stress, will increase the energy density in an area, in a volume. So whether you're using a normal stress or a shear stress, you're still applying that stress to increase the energy density in the target of the application. And so the cylinder here, again, you can see that there's torsion. If you have your arm around the neck and you are twisting, down at the bottom, the neck meets the shoulders, that part is not turning. So that's like the part of the jar that you're holding stationary. And then the twisting of the arm is where the rear naked choke is being applied up higher on the neck. And so you get this torsion, right? So it's like you're twisting the lid off of a jar. And that's going to apply a shear stress to the carotid sinus. So that's two ways of doing a rear naked choke. You can do it by squeezing, you can do it by twisting. And that's a little bit of the physics behind why those both work. And of course, if you want to maximize your effectiveness, you would use both types of stress. You apply both types, you both squeeze and you twist, which is happening in this picture. And you can see that it's definitely very unpleasant for this guy. So that was all I wanted to say about it's kind of a brief introduction to these physics concepts and how they apply to the rear naked choke. So thanks for listening. Please feel free to reach out to me if you have any comments or questions. You can reach me at this email address here. Thank you.